Continuando con nuestro evento, a continuación voy a presentar a Luna Lomonaco. Ella es profesora e investigadora del INPA, Brasil. Su área de trabajo es de sistemas dinámicos. En esta oportunidad nos va a contar sobre Making Quadratic Maps de Modular Group. Luna, adelante.
Muchísimas gracias por la presentación y muchísimas gracias por la invitación. ¿Tengo que hablar en español o en inglés? ¿Qué prefieren?
As you wish.
¿En inglés?
En inglés, como quieras, Luna. Sí.
Como quieras, Luna, tú. Sí.
Okay. So I will go to English because I realized that there was somebody not speaking Spanish. So if it is fine, I'll also for avoiding showing my Spanish deteriorating drastically since I moved to Brazil. Okay, and today I'm going to tell you of actually very long work. It started 10 years ago, joined with Sean Bullitt, and it's about mating quadratic maps with the modular group. And I promise you that by the end of the talk, you will know what is a mating between a quadratic map and the modular group. But very roughly speaking, a mating is an object that encodes dynamics of two different objects. In this talk, we're interested in an object that encodes dynamics of both quadratic maps and the modular group. Why? Because these are two different words, but not that much different. And it is kind of very cool that it exists another word where these two different words join. But before telling you all of this, I will give you a very gentle introduction about quadratic maps, the kind of quadratic maps we're interested in, at least, and the modular group. Okay? So let's start. Here, we are interested in the action of rational maps on the Riemann sphere. So the Riemann sphere, we all know, I guess, is the compactification of the complex plane, the union infinity. So you end up with a ball. And you are interested in iterating a holomorphic map, and in the Riemann sphere, they are rational, and see what happens. So we take our favorite rational map. A rational map, you write it as ratio of two polynomials. And you start iterating it on the Riemann sphere. What does it mean? You take a point on the Riemann sphere, and you consider the sequence of iterates of the rational map on that point. So zeta, r of zeta, r of r of zeta, r of r of r of zeta, and you keep going, is an infinite sequence. And you want to know what happens to this sequence. In particular, you would like to know if 2 points start nearby, do they stay nearby forever and ever? And in the case your family of map is equicontinuous, yes, by definition. So we can, we have that the action, the iteration of a rational map on the Riemann sphere gives a partition of the Riemann sphere in two sets. One is the set of points where the family is equicontinuous, or roughly speaking, the set of points that like each other's. They start together, and then they will stay together forever and ever. They are friends. And the complementary set is called the Julia set, which is the set of points with chaotic orbit. The set of points that don't like each other. If somebody does something, his friend nearby does the opposite. So let's make an example of this. Let's take, I forgot to say, we are considering in this talk rational maps of degree at least 2. Why? Because with degree 1, things are boring. If we start iterating a Mobius transformation, well, you have 2 fixed points, and depending on if they are real or imaginary, or if it is one with multiplicity 2, you have one kind of behavior or another, but that's it. And we know pretty well what can happen. So it's boring with degree 1. So we ask the degree of our rational map to be at least 2. And in this case, a lot of very interesting things can happen. And in particular, you always have points moving crazily. Your Julia set is always different from the empty set. But again, let's make an example. The easiest rational map of degree 2 is probably the polynomial zeta goes to zeta squared. And let's see what happens, who is the Julia set and who is the Fatu set for this map. We can see that if we take a point with modulus less than 1, so a point in the unit circle, in the unit disk, sorry, here, and we start iterating, well, the square of it is going to have a module even smaller, and the square module even smaller, and even smaller and smaller and smaller and smaller. It will converge to 0. Actually, all the points in the unit disk, when we start iterating them, they will converge to the unit disk, to the point 0. They will have modulus smaller and smaller and smaller and smaller and smaller. So the unit disk is part of the Fatu set. On the other hand, if we take a point with modulus bigger than 1, let's take the point 2. We iterate it, it has modulus even bigger. 2 goes to 4, which goes to 16, which goes to something even bigger. And we go to infinity. And if we take 2i, well, it will go to -4, that will go to +16, which will end up to infinity. And every point of the Riemann sphere minus the closed unit disk, under iteration, will approach infinity. Will get closer and closer and closer and closer to infinity. So this set, the complement of the closed unit disk, it's also part of the Fatu set. And so we are left with the unit circle, which I'm very carefully trying to show here. I almost manage. And what happens if we take whatever point on the unit circle and we get a neighborhood of it? Let's take the point 1. Okay, 1 squared is 1, squared is 1, squared is 1, is fixed. Now, we take a neighborhood of 1. We take 1 plus epsilon. It goes to infinity. 1 minus epsilon. It goes to 0. We take a point in the circle, let's say e to pi I over n to the whatever. No, to the whatever n, to the n plus 1, to the 45. After 45, iterate is going to come back. We take a point here, e to the 2 pi I theta with the theta rational. Well, this point minus q. Well, what happens to this point? This point will be started turning around forever and ever, but will never come back. He's going to come back, he will never come back. So, I mean, in a neighborhood of 1, they all hate each other, those points. If one point does one thing, the nearby does the opposite. They really don't want to stay together. And the unit circle is the Julia set for the map zeta square, the set of points with messy orbit, very roughly speaking. And another important thing I wanted to say here is that if you are in the Fatu set, which is the set of points that will behave, where the family of iterate is equicontinuous, by a theorem of Arzelà-Ascoli, this implies that your family of iterate is normal on a neighborhood. What does it mean? That every sequence has a convergent subsequence. If you are inside the unit disk, you converge to the function constant equals 0. Outside to the function constantly equal infinity. And this normality, we will see it later in a couple of slides. Okay, after speaking about rational maps in general, let's focus in an example of family which is very important to us, which is the quadratic polynomials. Why they are important for us? Well, because it is the easiest family of rational maps which is interesting, which has a degree at least 2, right? And well, if we have a polynomial acting on the Riemann sphere, we can see that infinity is always fixed. Infinity to the n plus c is infinity, right? And is attracting. We saw in the previous example that all the points outside the unit disk, the closed unit disk, goes to infinity. They are in the basing of attraction of infinity. If you have a very big number and you square it, complex number, and you square it and you do plus c, it goes closer to infinity. And so it has a basing of attraction, which is the set of points attracted by him, it, and we call it A infinity. Okay? In this context, it makes very well sense to consider the set of points with bounded orbit. The set of points that you can iterate forever and ever and ever. They will always stay there, which is the complement of the basing of attraction of infinity. And to this set, we give a name, we baptize it as field Julia set. Why? Because it happens that the Julia set is always the boundary of this set, and this set is actually your boundary field. This is because of the maximum principle. You cannot have holes there inside. And here I gives you some example of field in Julia set of members of the family zeta square plus c. This is for c equals 0 that we encountered before, is the map zeta goes to zeta square. Here for c equal 1/4. Here for c equal 1/4 plus epsilon. I manage, yes. Here is -1, and here is -1 plus epsilon. And these I don't remember by heart, because it has both a real and imaginary part, and I don't remember both of them. It's very, very, very clear. The first thing that you see is that 4 of these things are connected, and 2 of these things are disconnected. Actually, they are badly disconnected. They are counter sets. And so it makes sense to consider the set of parameters, parameter C, for which the field Julia set is connected. And to this set, we give a name Mandelbrot, and the Mandelbrot set is this guy. Now, 0 lives here, 1/4 lives here, 1/4 plus epsilon lives here, right outside. -1 lives here. This that I don't remember the parameter, but is the center of this component. And this lives here. So the Mandelbrot set is called the connectedness locus of the family. Is the locus of connectedness. For the parameter there, your field Julia set is connected. Makes sense, right? And something that will be extremely important here is if we are close to infinity, the plus C is not that important. I mean, 48 million plus, I don't know how millions I squared plus C. The plus C doesn't really make a big, it's not that important. And actually there exists a map called the Becher map, holomorphic, which in a neighborhood of infinity conjugates the action of your polynomial to zeta goes to zeta squared. Because this is the important part of the dynamics. The plus C is not that important. And it happens that if your field Julia set is connected, this map extends to the whole basing of attraction of infinity. So what does it mean? It means that if you are here inside, in your Mandelbrot set, your dynamics is zeta squared plus C in the field Julia set and zeta squared outside the field Julia set. And if your field Julia set is even locally connected, which is the case in these 4 examples, then the inverse of this map for Carat-Theodori theorem extends to the boundary. And why am I telling you this? Because if your field Julia set is connected and locally connected, the dynamics on the boundary is the dynamics of x goes to x. Because if you consider this map on the unit circle, well, you write zeta as modulus modulus e 2 pi I zeta, and when you square, modulus square is 1 goes to 1, and this goes to e to the 4 pi 2 pi I 2 zeta. So the dynamics on the boundary is the map zeta goes to zeta. This will be extremely important in 4 slides. Okay, now we leave something important I wanted to say here also is that quadratic polynomials are very hyperbolic, deeply hyperbolic. What does it mean hyperbolic in complex dynamics? It means that there is a metric that is expansive on the Julia set. Equivalently, it means that the critical points are attracted to attracting orbits. And if you are outside the Mandelbrot set, your critical point is attracting to the attracting orbit because it will not be part of your field Julia set. This is a theorem of Fatou. So every map outside your Mandelbrot set is hyperbolic. And the biggest conjecture in complex dynamics is that the interior of the Mandelbrot set is made by hyperbolic components. It means that every map in the interior is hyperbolic. This is the conjecture. If it wasn't the case, there will be in a queer component that is called queer because nobody saw it, ghost component, nobody ever saw it. So let's pass now to the parabolic counterpart of this family. So the family of easiest quadratic rational maps, but parabolic. And we are in the family pair 1,1, which is the family of holomorphic classes of maps of the form PA of zeta, zeta plus 1 over zeta plus A. Why we take classes? Well, because it happens that PA is holomorphically conjugated to P minus A. Every map here has fixed point infinity, which is parabolic, and the critical point at plus and minus 1 And P minus A has infinity parabolic and critical points at minus n plus 1. So it's basically the same map. And we don't want to keep track of both of them. So we consider the conjugacy class. But for everybody here, we have that infinity has a parabolic fixed point, and it has a basing of attraction, which is the set of points that will go to infinity. This basing is completely invariant. And then we can define the field Julia set in this case exactly like for polynomials. The set of points with bounded orbit, the complement of the basing of attraction of infinity. Just in the case of polynomial, infinity was super attractive, and here infinity is parabolic, but same thing. And the connecting, here there are, this is the field Julia set for A equal 1. And this for other two values. And this, all the three example, in all the three examples, the Julia set is connected, but again, we can define, this is not always the same, and we can define the connectedness locus to be the set of, actually parameters B, which is 1 minus A squared, in order to consider conjugacy classes instead of maps. And this is the set of B such that the corresponding PA has connected field Julia set. This is the guy. It's called the parabolic Mandelbrot set, which is homeomorphic to the Mandelbrot set by a result of Carsten Petersen and Pascal Hoche, which finally is in the archive. And something important I need to say here is that here, as for polynomial, you can encode what is the map, which is the dynamics inside the field Julia set with a map. In the case of quadratic polynomials, that map was zeta squared. Zeta goes to zeta squared. And in this case, that map is h of zeta, which is a zeta squared plus 1 over 3 over 1 plus a zeta squared over 3. This is a result of my thesis. And the important thing in this talk is that in the circle, these two maps are topologically conjugated. What does it mean? That on the Julia set, the dynamics of a quadratic polynomial and the dynamics of one of these guys is topologically the same, semi-conjugated, if they have locally connected and locally connected field Julia set. Okay, now after this very long introduction to the world of quadratic maps, we change completely world and we go in the world of groups. We consider PSL2C. What is this? It's the group of 2 times 2 matrices with complex entries and determinant 1 under the equivalent relations plus minus identity. The elements of PSL2C are Möbius transformation, that zeta goes to A zeta plus B over C zeta plus D with AD minus BC equals 0. And what we are interested in? We are interested in the modular group. And the modular group is a Kleinian subgroup, is a Kleinian discrete subgroup of PSL2C. What does it mean? Well, you take a bunch of Möbius transformation. I told you before that iterating one Möbius transformation is boring. So instead of iterating one, we take a bunch of them and we compose them in all possible ways, and we see what happens. This is a Kleinian group. And for Kleinian groups, the dynamics of a Kleinian group also gives the partition of the Riemann sphere in 2 sets which are invariant and complementary. One is the ordinary set, which is the set of points in the Riemann sphere where the elements of the group form a normal family. and the limit set is its complementary. In this talk, we are interested in the modular group, which is one particular cleaning group, is PSL2Z. This is a cleaning group with generators tau1, which is zeta plus 1, and tau2 of zeta, which is zeta over 1 over zeta. Here, I put the tessellation of the upper half plane for the modular group. For the modular group, the ordinary set is the upper and lower half plane, but the same happens upper and lower half plane. So we usually just show the upper half plane. And the limit set is the real line. And here you see a tessellation. This is a fundamental group, a fundamental domain in gray. You see that after tau1, this will cover all its translation. And under tau2, this will go here. If I well remember, that will go, and then after tau1, it will cover all of this. And then this one will go here, if I well remember. Well, I don't remember exactly who is mapped to who, but I mean, this will cover this and this and this. Somebody with open microphone, if you could close the microphone. Okay, I managed myself. Sorry, Elton. I mean, this one after this map will go here and then here and then here and then here, and after zeta plus 1, it will cover the rest. Okay? So these two words of rational maps and Kleinian groups are not that different. And this was realized by Sullivan in the early 80s. And or late 80s actually. And in both cases, the action of this object gives a partition of the Riemann map in one set, which is where the points are well behaved and like each other, which is the domain of normality, which in the case of rational map is called Fatou set, and in the case of Kleinian groups is called ordinary set. And the complementary, which is the set of points with messy dynamics, which in the case of rational map is called Julia set, and in the case of Kleinian groups is called limit set. And these are really the first two entrants in the dictionary, in Sullivan's dictionary, which is something pretty powerful and super cool actually, which is a dictionary of correspondences between these two words. And okay, these two words are not that different. Actually, there exists an object that can be both. That can be a map and that can be a group, a Kleinian group. Now, since a map is not a group and a group is not a map, we have to leave the word of maps and group and entering the word of their minimum common multiple in some certain sense, which is the word of holomorphic correspondences. What is a holomorphic correspondence? A mess, but I will try to explain to you in easy ways. So holomorphic correspondence over the Riemann sphere is a multi-valued map defined by a polynomial relation, by the zero of a polynomial. So in this talk, we are just interested in two holomorphic correspondences. This meaning that every zeta has two images, 2W, and every W has two preimages. And for this to happen, we need a polynomial in degree 2 in zeta and 2 in W. And we consider its zeros. And this gives us algebraic surface, right? This is P of ZW equals 0, where my P zeta W has degree 2 in zeta and 2 in W. And who is going to be my correspondence? Well, we take the projection on the Riemann sphere where my zeta lives. This wanted to be a Riemann sphere, not a smile, but I mean, maybe it's a smile. And this is the projection where on the Riemann sphere where W lives. And the correspondence, the holomorphic correspondence, is the multivalued map associating to zeta W. So for each zeta here, there are 2 W here that kills the polynomial, right? Because the polynomial is in degree 2, in zeta and W. And these are the 2 images. And for each W here, there are 2 zetas here above that kill the polynomial. One was this, and one, let's say that is this one. And these are the 2 preimages. So we start iterating this thing, and at the third iterator, you want to cry. But it makes very much sense. Why? Because you can write a rational map as a correspondence. If your rational map is p zeta over q of zeta, you just take the polynomial wq zeta minus p of zeta. The zeros of these polynomials defines a correspondence which is n to 1, which is a map. And if you have a Kleinian group with generators, these things, please read, not make me pronounce this. You can write them as a correspondence by taking, well, the polynomial that kills each term. So these things are cool because they can be a rational map and they can be a polynomial. And now the question is, can they be a rational map, and a group at the same time? A correspondence can be a map, a correspondence can be a group. Can they be both at the same time? And this question started being investigated by Sean Bullitt and Chris Penrose in the early 90s, because they were plotting limit sets of particular family of correspondences, and they saw this. And this looks like what? Well, it looks like 2 copies of the field-Julia set of a polynomial, pa and pa, looks like 2 copies of this, with wrapped around the tessellation of the modular group. These things you wrap around. So they started wondering, okay, can we mate quadratic maps and modular group in a correspondence? So, what is a mating? Very roughly speaking, a mating between 2 objects A and B is an object C behaving like A on a invariant subset of the domains and like B on the complementary. And these things exist, matings exist in the world of polynomials. You can make 2 polynomials mateable and it gives you a rational map. And Arnaud Cherita has very, very, very nice Arnaud Cherita on its webpage has very beautiful videos of polynomials mating, and with whom you get a rational map. And the matings also exist in the world of Kleinian groups. Actually, they started in the world of Kleinian groups. And then I started wondering, do these things exist also in the world of, can we mate a map and a group? A quadratic polynomials, they thought it was this thing, because it was look like. And then they say, well, they started defining a mating between a quadratic polynomial and the modular group as Well, a two-to holomorphic correspondence, because, well, if you wanted to be both, you better take the object that can be both, for which there exists an invariant open simply connected region and a conformal bijection conjugating the action of your correspondence on this set to the action of the generators of the modular group. And on the complementary is the one-point connection of two sets, lambda minus and lambda plus. And on lambda minus, we have a homeomorphism conjugating the action of your correspondence to the action of a quadratic polynomial. And on lambda minus, we have a homeomorphism conjugating the action of your correspondence to the action of the inverse polynomial. This is what they defined. And then they started wondering, okay, do they exist? I forgot the question mark. And well, this question really has two sides. On one side, it's, can we mate quadratic polynomials and the modular group? This is the dynamics of a quadratic polynomials on its boundary, on the boundary of its field Julia set. This is on its Julia set, matches with the dynamics of the modular group on the real line. Because I mean, if we want this to be a quadratic polynomial and this to be the modular group, this thing is holomorphic. So I mean, the two dynamics should match on the Julia set. In other case, we have problems, right? So this is the first question. Then the second question is, there exists some correspondence that could realize, do we have a candidate correspondence for doing this? And these are something like, is it possible questions? And we have the questions, okay, do they actually exist? So, is there exist a family of correspondences such that every member of this family is a mating? And in the case, the answer is yes. Does this family organized as the model family? Or said in different ways, is the connectedness locus of this family homeomorphic to the Mandelbrot set or to the connectedness locus of the rational map we made? These are the questions. Now, I will answer you briefly these two, which are both yes, and were answered by Sean and Chris. And then I will answer also briefly, looking at the time, these two that are also positive and are work of me and Sean. So, in 1994, Sean and Chris proved that the modular group and quadratic maps, quadratic polynomials, fit together. There exists a homeomorphism, which is the Minkowski question mark map, actually a bit modified because the Minkowski map will go between 0, 1 and 0, 1 is extending, which is an homeo which sends a real number written in continuous fraction expansion. So you take x0 plus 1 over x1 plus 1 over x2 plus 1 over x3 plus 1 over blah, 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 blah. You continue. To its image written in binary. You write 0 dot x naught copies of 1, followed by x1 copy of naught, followed by x2 copy of 1, followed by x3 copied of naught, and continue like this. And why we speak about that? Well, because this map conjugates the action of the generator of the modular group on minus infinity 0, so the negatively real axis, with the doubling map. X goes to 2x, which is, we say, the map that encodes the dynamics of a polynomial on its Julia set, if your Julia set is locally connected. And on the positive real axis, this Minkowski map conjugate the dynamics of the generator of the modular group to the halving map, which is the map that encodes the dynamics of a polynomial, of an inverse quadratic polynomial on its Julia set. Now, I'm lying in the sense that everything is much more complicated than this. You have 6 commuting diagrams. I mean, just it's very easy to suspect, because I mean, the negative real line is not invariant under theta 1, because you go to minus infinity plus 1. It's all more complicated. But at the first approximation, this is what happens. What you can do, actually, you can fit here the field Julia set of a quadratic polynomial, and here the field Julia set of its inverse, and wrapping the modular group around. This topologically is possible. This is what they proved. You have this map that glue the dynamics for you. Then the second question is, okay, you can do this, very nice. Is there a family that's a candidate family? And yes, it's this family of holomorphic to correspondences. And I could explain why, but it will take me at least 10 minutes. The very, very, very short reason why we end up with this family is that if you write the modular group as a correspondence, it satisfies some relations. And if you want your correspondence to be acting like the modular group on an open set, it's better to keep respecting those relations. And you make computation and you end up in this family. And in this family, I here showed the limit set, which I will define in the next slide, of 3 different members of this family. So it happens that for every member of the family I showed you before, it's this, which we just called FA because it's very long, the analytic expression. So family FA, for every member, for every A, 0 is a parabolic fixed point. And you have a half plane which is invariant under the correspondence, and where the correspondence acts like a 1-to-2 map. So the image of this set under the correspondence is, I'm going to put it blue, not because I don't have it, so I'm going to put it green, is this set. And this line, the imaginary axis, is sent to this line and is sent to this line. And then the image of this thing under the correspondence, it's inside this disk, and again it's 1 to 2. And you can define the forward limit set to be the intersection of all the images under your correspondence of this half plane. It happens that there is an involution between this part and this part, which conjugates the action of FA, which the action of the inverse. Hence, restricted to the pre-image of this half plane, your correspondence is a 2-to-1 map. So this is 2-to-1, and it's a map. So this line goes to all the imaginary axes, and this line alpha goes to all the imaginary axes. And you can define the backward limit set as the set of pre-images of this half plane. Okay, and this point is parabolic for everybody. And here I show the limit set, and the limit set is the union of the forward and backward limit set. And these are the limit set for some member of FA, of our family of correspondences. This is disconnected. All the others are connected. And well, some are connected, this is disconnected. You can define again the connectedness locus for this family, which is the set of parameters A for which your limit set is connected, and this is the guy, what we call the modular Mandelbrot set, which kind of looks like the Mandelbrot set. And they conjectured, Sean and Chris, that the family, our family of correspondences FA contains a mating between the modular group and every quadratic polynomial with connected Julia set. And then the connectedness locus, modular Mandelbrot set, for this family is homeomorphic to the Mandelbrot set. And they tried for 20 years to bring home the result, and they managed that to prove that there exists a mating between the modular group and quadratic polynomial in the family FA for a very big class of value C, but they didn't manage to bring the result home. They didn't manage for everybody. Why? Because all these results are done perturbatively. They start, I told you before that for everybody here you have a parabolic fixed point. And they start by breaking this parabolic fixed point, perturbing your correspondence. You break the parabolic fixed point. And then you use something that is called polynomial-like mapping. That is what you use in the moment you want to end up with a polynomial. And then they try to pinch back with Eisinski surgery in order to prove that you have mating between modular group outside and the polynomials inside. But the surgery for coming back doesn't really work always. And anyway, I mean, you have a family with a persistent parabolic fixed point. And you try to prove that everybody in that family in a subset of the domain invariant behave like a polynomial, where polynomials are hyperbolic maps. So this makes you wonder, maybe this family FA consists of mating between the modular group and a family of quadratic rational maps, but family parabolic with a persistent parabolic fixed point. And this is the case. The model family is not the family of quadratic polynomial, it's the family of pair 1, 1, family of maps zeta plus 1 over zeta plus a. And the result is the following. Well, we define now with Sean a mating between the rational quadratic map of the form of this form and the modular group as a correspondence such that restricted to an open set, you are conformally conjugated to the action of the generator of the modular group on the upper half plane, and on the complement in a doubly pinched neighborhood of your backward limit set, you are conjugate to the dynamics of hybridly conjugate to the dynamics of a map of the form PA. And if you know this one, you know that in the same happens in a doubly pinched neighborhood of the forward limit set. And the result is that for every A in the connectedness locus, the correspondence is a mating between some rational map of our family and the modular group. And this is a slide that shows a bit gives an illustration of the result. This is the modular Mandelbrot set. This is the parabolic Mandelbrot set M1. This is the center of this component, the period 1 component. This is the center of the period 1 component. And there is here around your correspondence is hybrid conjugate to the maps PA of zeta in a pinch neighborhood here. This guy is the center of the period 2 components, which is the model for the center of the period 2 component here. And this is the center of the period 3 component. And there is a doubly pinch neighborhood where it's conjugate to the center of the period 3 component here. And in the last 4 minutes, in the dynamic plane theorem, we have that for every A, the correspondence is a mating between the modular group and some rational maps. And it's easy to prove that this rational map is unique. And this induces a map between the modular Mandelbrot set and the parabolic Mandelbrot set, such that it associates to each parameter A, the A, such that your correspondence is conjugate on a pinch neighborhood of your backward limit set to the map PA of zeta equals zeta 1 over zeta plus A on a pinch neighborhood of its field Julia set. And we finally proved that this map is a homeomorphism, which is dynamical. It means that if I associate A and A, then the restrictions of the objects are conjugated. It's conformal on the interior of the modular Mandelbrot set. And moreover, it extends to homeomorphism between open sets, avoiding a neighborhood of the root. So from here to here. And as a consequence, we get that the modular Mandelbrot set is homeomorphic to the Mandelbrot set using the result of Carsten and Pascal. And we also needed for the result, for the dynamical theorem result, to prove that here outside, you are conjugated to the modular group on the upper half plane. And in order to do that, and doing that, we ended up constructing a dynamic theory for these guys that completely parallel the dynamical theory of quadratic polynomial made by Dwelly Hubbard. It would parallel, the model maps are the parabolic rational maps. So this theory should be modeled on the theory of parabolic rational maps. But since polynomial have a much better understood theory, we modeled it on it because we had more to say. Anyway, as for polynomial, polynomials have a Butcher map that sends the complement of the field Julia set when it is connected to the complement of the unit disk, and it conjugates conformally the dynamics on the complement of the field Julia set to the dynamics of the map zeta goes to zeta square on the complement of the unit disk. In our case, we have a Butcher map that goes between the complement of the limit set, in the case the limit set is connected to the upper half plane, and conjugate the dynamics of your correspondence with the dynamics of the generator of the modular group. And in the case of polynomials, there are a lot of interesting things that you can do with this Butcher map, because when you know that you have that the dynamics of your polynomial is conjugate to the dynamics of zeta goes to zeta square by something conformal. Well, here you have two foliations given by concentric circles and raised with constant argument, which you can pull back via the Butcher map, PC. And the pullback of these rays under the Butcher map are called external rays. And they are very useful tool for studying your field Julia set. And in particular, we have that a periodic ray's length, and every repelling fixed point is the landing point of a periodic ray. And in our case, we don't have this, but we have a map going to the upper half plane, conjugating the dynamics outside the limit set to the dynamics of the modular group. And on the upper half plane, you have geodesics, periodic geodesics, which are geodesics that come back after a finite number of type 1 and type 2, which you can come back by your Butcher map. And it turns out that periodic geodesics land, and every repelling fixed point is the landing point of a periodic geodesic. This was very difficult to prove. And with this, we also had a Jacobs inequality, just for the first level, but which is better than the original Jacobs inequality, which basically tells you that what's the difference here between this formula and this formula tells you that the ratio between this, the balls attached, the copies attached to the pieces of the Mandelbrot attached to the main cardio and the Mandelbrot is bigger than the ratio of the pieces of the modular Mandelbrot set attached to the main cardio, which is not a cardio, and the whole modular Mandelbrot set, which is this, what is attached shrinks more in our case than in the case of the Mandelbrot set. And of course, the dream will be generalize this and say something about the local connectivity, but yeah. So far, so good. Where is the, no. Thank you for your attention.
Muchas gracias, Luna, por la charla. Muy buena plática. Por favor, podemos abrir los micrófonos. ¿Puedo un aplauso a Luna, por favor? Preguntas, comentarios para Luna. Question, comments.
No sé si puedes hacer cosas en grado más alto o no. O solo tiene que ser en grado 2.
Se puede intentar hacerlo en grado 3. Ahí probablemente vas a tener 3. No vas a tener 2 copias del limit set, tendrás las 3 probablemente. Y en lugar que hacer el mating con algo de un grupo modular que tiene 2 generadores, tendrás que ir con grupos kleinianos que tienen 3 generadores, yo imagino. Pero sí, se podría recomendar de 0 con otro grado.
Pero en grado 3 también existen los intertraining. No sé si hay algo similar ahí, que existen más estructuras.
No sé, Mateo. Te decía, sé contarte de esta familia. Hay mogollón de cosas que se podrían hacer. Eso es un mundo. Pero bueno, solo conocemos bien esta familia.
Sí, porque si existen intertwining por polinomios, a priori tal vez habría una manera de definir como intertwining para en el mundo kleiniano o algo así. Sería interesante. Yo
Sí,
creo.
sería.
Luna,
¿Sí?
sí, gracias por las charlas, muy bonita. A ver, tú has producido un mating entre el grupo modular y esta familia de cuadráticas. ¿Es la única mating con cuadráticas que puedes producir con el grupo modular? ¿O
Con
puedes
el
también producir?
modular sí, pero mira, esto que te dibujo es el discreteness locus de faithful representation and discrete of C2 times C3 groups. ¿Qué te estoy diciendo? Grupos tales que generados por 2 chicos, por 2 mapas, por 2 mapas, tal que un sea orden 2, el otro sea orden 3. En nuestro caso, el grupo modular vive aquí, porque lo puedes escribir de forma diferente. Le mudas los generadores, uno de orden 2 y uno de orden 3. Estos de aquí son los parabólicos. Pero Sean demostró con Hardy que hay muchas familias de correspondencias holomorfas que realizan mating entre grupos aquí y la familia cuadrática de polinomios. Porque estos aquí dentro son hiperbólicos. Y ahí todo bien. El moral de mi charla es hiperbólico va con hiperbólico y parabólico va con parabólico. Si tenés el grupo modular es bien parabólico. Mira los generadores y mira la teselación, es el festival de la cúspide. Entonces ahí tenés que cruzarlo con una familia cuadrática parabólica. En cuanto existe mating de la familia cuadrática, pero con otros grupos kleinianos. No con el modular, porque ahí consigues en algunos puntos, pero no consigues hacerlo todo porque por un lado tienes cúspides, por el otro no. Y cúspides y no cúspides nunca se llevaron bien, digámoslo así.
Entonces es esperable de que si yo tomo cualquier grupo fucsiano, por ejemplo, finitamente generado de primera clase, no tenga por qué producir un mating con alguna familia de funciones racionales.
No tenés por qué.
No tendría por qué.
Tenés que mirártelo de caso a caso. Ese
Oh.
es el primer ejemplo, si queremos.
Ok. Gracias, Luna.
Nada.
Camilo, ¿quieres preguntar algo?
Sí, tengo 2 preguntas. De
Dale.
hecho, van en dirección a las que ya echan los profes. Sí, mira, a mí me interesa mucho este tipo de cosas, pero en el sentido de, tú estás hablando de funciones racionales. ¿Se ha estudiado algo, se sabe algo cuando tú tomas funciones trascendentales? Por ejemplo, el seno complejo o el coseno complejo. Esa es una, perdón, pero voy para la otra ya después esto me responden, ¿no? Sí. Porque la otra depende de si eso tiene sentido o no tiene sentido. Tú das una relación entre grupos fucsianos y polinomios, ¿sí? Entonces, probablemente yo puedo tomar una función trascendental y la veo como un producto infinito, ¿sí? De zetas menos a adecuados. Entonces, ¿será que se puede extender de alguna manera razonable esos resultados de tal manera que tú asocies ya no un grupo kleiniano finitamente generado, sino infinitamente generado? Que
Genial.
ahí es donde aparecen las superficies de tipo infinito en ese caso.
Muy buena pregunta, Camilo, ¿no? La respuesta honesta es no tengo ni idea. ¿Has sentido? Lo que pasa es que yo sepa hasta el diccionario de Sullivan está en grado finito. Entonces ahí ni tenés el punto cero de comienzo. Estás mudo.
Sí, 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 ese diccionario, sí, sí.
Entonces no sabría ni por dónde comenzar. Bueno, tal vez sí sabría por dónde comenzar. Es algo interesante, pero no tengo la respuesta.
¿Y sabes si alguien la ha intentado o al menos ha dicho, mira, aquí hay
Que yo
un primer
sepa,
acercamiento?
cosas que yo sepa, esta de aquí fue la primera familia. Espera, acá de la familia. Oh, familia, aquí. Esta de aquí fue el primer ejemplo de matings entre mapas y grupos. Y luego tomaron el detour con este resultado. Este resultado es muy lindo. Es aquello que te decía de entre mapas polinomios cuadráticos y otros grupos faithful representation of C2 times C3 groups. Y luego no me parece que yo sepa, no hay más cosas. Hay otros puntos de vista de estudiar correspondencias, pero no como meetings.
Gracias.
¿Más preguntas, consultas para Luna? El chat no veo. Si no hay más consultas, damos un aplauso nuevamente a Luna. Muchas gracias, Luna. Muy bonita plática.